April 20th version of the Brown Bag webinar. Really appreciate the opportunity that we've been given to present to y'all. I hope it's good, and we are going to dive in. As Rachel mentioned, my name is Rob Alley, and I'm an engineer with Elrod Engineering. For those of you who don't know us, our company has been providing sign design and structural engineering services since the 1980s, and we are proud to be a long-time member of MSSA. I'm very thankful for this opportunity to share just a bit with you about the engineering side of your signage and architectural element world. I appreciate you spending the next hour with us as we give you what will hopefully be a helpful overview of what goes into sign engineering. I don't intend to make an engineer out of you, but in our experience, if you as a project manager have a good basic understanding of what goes into the design of a sign, you'll first off have a smoother working relationship with your engineer, and secondly, be able to better serve your client, which is much more important. This is the first of a two-part introduction to sign engineering. We will address freestanding signs, including existing signs, in 2 weeks. We'll hopefully have time for questions at the end, so let's get started. As I mentioned, 2 parts today: sign engineering and wall signs, and then in 2 weeks, freestanding signs with existing sign structures and a focus on inspections being our focus. So what is sign engineering? The 2 main topics that I want to cover today in part 1, theory and practice. The engineering theory is basically what drives the design. And then for today's webinar, the practice will be a focus on wall signs, what information is needed by your engineer, and frankly, what makes a good engineering request. So talking about the theory behind this, the building code is really what drives most aspects of the engineering design of signage. It basically tells us what and how loads are applied to a sign. It is locally dependent, even though sometimes if you don't have a local building code, it would default to the statewide building code, but it can vary widely depending on the region where you're working. I like to give an example of Texas, where statewide, the building code is a 2003 version of the IBC, but several states are already on the 2018 and even 2021 version of the building code. There are states, depending on where you work, that have specific state building codes. North Carolina is an example of one that pretty much just wholesale adopted a version of the International Building Code. But then you have a state like Florida, which made a lot of adjustments. And really, as a result, that was a result of the fact that so many hurricanes hit Florida, they needed some unique things built into it. I always like to point out Disney World. They have their own building code. The Epcot building code addresses not just signage in the Magic Kingdom, and it does address that, but also things like roller coasters, castles, and many other things that you never would have thought about. But ultimately, why does the building code matter to you as a sign company? Basically, a sign that you build for one location may not be properly designed for a nearby city. We see this the most often when you have 2 cities that have, one of them has the 2009 version of the building code and the other is a 2012 or more recent. Those building codes, and particularly use an example of the 2009 and 2012, those building codes take very different approaches to the analysis, and so they aren't identical, the results. Basically, if you have that design for 2009, you have to do a new design, even though they're close to each other and you think things might be similar. One thing that surprises me is that cities do not view codes as backwardly compatible. So, for example, even looking at the 2012 through 2021 versions of the building code, you would think that those are essentially the same when it relates to signage, those building codes. Some slight variations, but nothing really significant. You would think that if you had a design done to the most current one, the 2021 version, it would be good in all the other locations. But cities, if their regulations say they require the 2015 version, you have to have it done to the 2015 version. That needs to be on your drawings and on the calculations. This is particularly important for clients that may have a pre-designed family of signs that are installed across a large region or even nationally. We're working with a client right now, an end user who does, they're a nationwide retail chain, and they had their family of signs designed to the 2012 building code, and are having to update everything because that's what they were done to, that's what the analysis states. And so they can't just take those drawings and put the local address on it and submit it. It has to be updated for site-specific usage. So this is a comparison of the building code. As you can see, building codes reference design manuals that are prepared under the oversight of the American Society of Civil Engineers, or ASCE. The ASCE design manuals tell what and how loads are applied. It tells us how to do the analysis. I'd like to make the point that just because something has stayed up in the past or has always been built a certain way doesn't necessarily mean it is properly engineered. We'll talk about this a bit more a little later, but wind loading is a good example. Signs typically have to withstand a 115 miles per hour wind. I'd be willing to bet that nobody listening to this webinar has actually experienced 115 miles an hour wind unless you've driven an unshielded motorcycle at almost twice the speed limit. That wind force is what we need to design signage for. Of course, making things simple, the building code is on a roughly 3-year cycle, and the design loads and design manuals are on a roughly 5-year cycle. So they're out of sync, and you've always got to match those things up. But your engineer will be on top of this stuff and make sure you've got the right design being done for your site. So pressing a little bit deeper into the theory of signage design, the other two factors, in addition to the building code, that has arguably the most impact on design loads are the risk category and the exposure category. Risk category is ranked 1 through 4 and basically describes the use of a structure and how critical it is. Or to put it another way, what are the consequences to human life in the event of a failure of that sign? There are 3 exposure categories that essentially describe the surrounding topography and therefore how the local wind loads may be adjusted. It should be noted that there originally was intended to be an exposure category A, but basically the committee determined that a very heavily built up urban area with tall buildings was just too complicated to model, and that you would either have to do a wind tunnel study on your specific building or just assume exposure category B. This slide shows literally what the building code says about risk categories. But what do you as a project manager need to know? Let's look at another slide. This lays things out in, I think, a little more readable, understandable, digestible version. Signage is generally risk category 1 or 2. Most people will classify a small to medium-sized freestanding sign as risk category 1, even though the local jurisdiction may feel otherwise. Large freestanding signs or medium-sized ones located near crowded areas should almost always be risk category 2. Any sign that is attached to a building, channel letters, wall signs, blade signs, whatever you've got, should be risk category 2, unless the building itself is risk 3 or 4. So risk category 3, a stadium, a lot of school buildings, some large hotels, because there's more people in a concentrated area, they would be risk category 3. And so the assumption or the default is that any signage in one of those venues would need to be risk category 3. Not necessarily 100% of the time, but that's the general assumption. So what about exposure categories? As I mentioned before, the exposure category is a reflection of the topography in the surrounding built environment. Essentially, you could think of this as a measure of the roughness of the ground. As an example, I enjoy whitewater rafting, and I often think of this in terms of river flow and rapids. The faster the water, the more force it imparts. But when you have a rough river bottom, the water tends to slow down. Fast fluid flow equals more force. Slow fluid flow equals less force. Air is a fluid and operates as such. I'm summarizing for our presentation, but you can see from the description on the slide what we as engineers have to consider in determining the exposure category. Exposure category C can be considered the default setting, open terrain with scattered small structures. Exposure B is a more built up area. You can see from the photograph, typical suburban area. This built up area, because you have a consistency of one single, maybe 2-story split level type buildings, is more consistent. So this disrupts the flow of the wind, and therefore that turbulence that's created is slowing down the wind, and therefore the wind load that's applied to a sign can be reduced slightly. This is another example of exposure category B. Again, bigger buildings, you're creating this turbulence, it's slowing down, so there's less force that's applied. Going the other direction, exposure category D actually results in an increase in the wind loads that are applied. It's basically located on the edge of a flat, unobstructed area. Other than coastlines, this isn't terribly common, though you could run into it in areas of the Midwest, such as along the Great Lakes, or even other non-Great Lakes, if the lake itself is big enough. We have also seen this a few times in New Orleans, based on the orientation of the sign to the Mississippi River itself. One of the things I like to point out about this photograph, this aerial photo of Miami, is that you can see all three exposure categories in one photograph. If you look in the center along those barrier islands where Miami Beach is, that's exposure D. You've obviously got a large unobstructed area to the right, being the Atlantic Ocean. The wind's coming in and it's at kind of its highest pressure. Then you move to the contained within that pink outlined area. That's exposure category B. So that's the main part of downtown. You've got all those large buildings. So the wind is being slowed down. So you've got a lower wind pressure. And then you get outside of that. So kind of in the northern parts and over along the left side of the photograph, that's exposure C. So kind of that default medium wind pressure that's being applied there. So a lot of theory, a lot of whys and wherefores. So now we're going to get a little bit more into the analysis and start talking about loads that are applied to the sign, which your engineer will need to be considering. Two main concepts. We've got dead load, and then the next three are considered live loads. Dead load is just a constant load that doesn't change. And then a live load is variable. It can change. The three that I've got listed here are the ones that apply to signage. There are other live loads that apply to structures that don't apply in our cases. Basically, dead load is the weight of the sign itself. That's a permanent load, and as you know, it won't change. The sign is what it is. These live loads that will need to be considered, the first is the wind load. That is basically a force that's being applied to the sign due to the wind, which pushes, pulls, and acts both ways. You can tell engineers were real creative in how we name things. The snow load will probably not be a factor unless you have a very wide sign cabinet and you're in a location that gets a lot of snow, or if your project is a canopy or an awning. Seismic load is, not surprisingly, due to earthquakes. Mainly people think of, and it's mainly applied in California and Illinois, though there are certainly a few other areas. West Tennessee being one that comes to mind, where seismic loading does need to be evaluated as part of a design. A little bit more about the wind load. As I mentioned, it's the force that's being applied to the sign due to the wind. The design manual that's the most current is ASCE 7-16. So the 2016 dated version. that has altered the wind maps and the calculations slightly that are being used to calculate your wind load. This slide highlights some of the details, some of the highlights of changes in this most recent version. Mainly, the changes to the wind maps were focused on non-hurricane areas, so the inland parts of the United States, and it resulted generally in a decrease in wind speeds, except along the coastlines from throughout the Gulf and then up through the North Carolina coast. The wind speeds, and we'll show some examples of these in a minute, but the wind speed maps presented in the design manual are based on a statistical analysis of roughly 50 years of actual data. Therefore, they do change with time. More detail than you want to know, but just for completeness, one of the other biggest factors is a pressure computation. So the people in charge of the design manual acknowledge that at higher elevations, the air is thinner. And so that results in lower pressures. And so there's an adjustment for that lower air density at higher elevations. So this shows the wind speed maps that are pulled from the design manual. And this is where things are really starting to get applicable to the work that y'all are doing. Unless you're viewing this on a large screen, I admit that it may be hard to read, but I want to focus on the interior of the United States. On the left map, the 7-10, so kind of the previous version, most everything in the interior of the United States is 115 miles per hour. If you look at the current one, the one on the right, you can see that there are areas, several areas with lower wind speeds than that. Much of it, the country, is actually less than 107 miles per hour, which may not sound like much, and especially if you're looking at some channel letters, say, fairly small area, they're attached to a wall. That difference in wind speed probably isn't going to make much of a realistic difference in how you're attaching to the wall. But if you've got a large freestanding sign, say one of these interstate signs where you've got a 400 or 500 square foot cabinet and it's 120 feet up in the air, that can make a significant difference in the loads that are applied, which means you may wind up with smaller steel, a smaller foundation, and so the actual cost could be impacted fairly significantly. I do want to just point out, just for your information, you'll notice there's some gray areas. They may look like smudges, but those are areas where you're typically having along mountain ranges or sometimes within interior to mountain ranges. Those are special wind zones where, due to the topography, a local wind study was required and has been conducted. Biggest difference, a good example of that is in Colorado. Denver, down on the plains, would be 105 miles per hour for risk category 2. But go not very far to the west and you get into what's called the Pikes Peak building area, and the design wind pressure or design wind speed is 135 miles per hour. So big increase by going not very far, but it's because you're going up into the mountains. This is a comparison of wind speeds just for context between the old design manual and the current ones to show how things changed. Particularly, this is applicable to your clients who have families of signs, so that if you have a master brand book or even brand books that are being pulled from a large region, those may need to be updated. But for example, in Nashville, that risk 2, so for anything attached to a building, the wind speed dropped from 115 to 105. Same for Huntsville. Mobile, it stayed the same, not surprisingly, because it's along the coast. Mexico Beach, Florida, same thing. It stayed at 133. So again, the changes were focused mainly on inland, non-hurricane areas. I like to point out that, just as a reminder, these are design wind speeds. Mexico Beach, y'all remember a few years ago when Hurricane Michael came ashore, it devastated Mexico Beach. It hit landfall at over 150 miles per hour. So even though everything was designed properly, if it was designed to those wind speeds of 133 miles per hour, nature threw something at the city that it just wasn't prepared for, and the results were not surprising given what the hurricane did. This is a map of snow loads across the United States. Most people in the South don't really think about snow loads. Doesn't snow much. I think Nashville this year, we got one flurry, and even that didn't really do much. And on top of that, a sign doesn't really have much flat area to keep snow. But what about awnings and canopies? I know a lot of times your projects may include these. It's a whole side note about changes in the building code that relate to the design of awnings and canopies that are surprising to people. But snow load, when applied to an awning and canopy, can be significant and can even control the design as opposed to the wind. You would think 115 miles per hour wind speed would be the controlling factor, but sometimes a fairly relatively small snow load may be more significant. The detail on this is pretty small, but for example, most of the South is 0 to 5 pounds per square foot. The gray area is 0, and then as you go from the dark purple in the lower part of the South towards lighter colors, the loading is increasing. There are parts in Tennessee where you have a 20 pounds per square foot snow load. I'll discuss it a little bit more in the second part of the session, but this snow load is often what surprises people that we work with. This is a visual representation of how significant seismic reactions can be. We're all aware of how active California is when it comes to earthquakes. And again, you look at the graph and it's not a surprise that much of California is red or brown in color. But don't forget that the New Madrid fault line along the Mississippi River is potentially the most significant, or another way to put it, the worst potential seismic zone in the United States. All right, so let's get to the fun stuff. Let's talk about signage. We're going to dive into wall signs, giving you an overview of some of the different types. And with each of those types, I'll point out a few things that your engineer will hopefully be considering. Admittedly, we are only touching the surface. And again, I'm not trying to make you an engineer. I just want to open that window a bit to help you better understand some of the design factors that underlie your sign project. So a lot of people use a lot of different names and terms, and I think it's important to make sure we're all speaking the same language and using the same definitions. So first, a wall sign is simply a sign or a cabinet that is connected to something, either a building wall, or just some other wall flat surface. I've listed some common terms for types of wall signs here. Another term, which I don't have listed, but I see clients use sometimes, is a fascia sign. Technically, a fascia sign is a type of wall sign. A fascia sign is mounted flush to the wall, and a wall sign is just more general. It's literally a sign that's attached to the wall. Channel letters, as you know, are shaped signs that are typically lightweight and have small surface areas to the wind. A blade sign projects out perpendicular from the wall, and a hanging sign, or some people call that a bracket sign, hangs down from a canopy, a ceiling, or other overhead surface. So you can have a hanging sign. A hanging sign is coming down from a surface that's above it. A blade sign can project out and then hang down. There's some slight definitions. Really, why is this important? As you have probably experienced, some cities have got very particular sign codes, and so they may have a hanging sign allowance, and you just want to make sure that your sign meets that definition and that it's not considered a different type of sign, just as an example. So those terminologies and the way the definitions show up in the sign ordinances is really important to make sure you're familiar with that. So this is an example of a wall sign, and it's frankly about as simple as it gets. This is a flat cut shape, flush mounted, lightweight, and pretty simple. It's an open frame sign. It actually does pose a bit of a mounting challenge. So what was important in this case were two things. One, we needed to know from our client, what was the wall type? So the surface of the wall, and then what was behind the wall, so that we could specify the connections and if blocking was available to be installed or not. And so that determined the mounting method for the sign. Or were there, again, kind of communicating with them, are there any mounting limitations that we need to know? Because there's several different directions that we could go. But the other thing about this that made it a challenge, and this was communicated to us from our client, was that the main issue here was that the sign had to be designed to withstand over-exuberant fans from trying to take it with them after the Golden State Warriors won a game. Flush mounted channel letters, and again, this is pretty simple. It's just letters and shapes mounted flush against the wall. Question that would lead to is what type of wall? For efficient completion of the engineered drawings and analysis, it really helps when you can provide that wall type information to your engineer. The ideal is if you can get architectural drawings or structural wall drawings from your client. Those may not be available. A survey may have to be done to determine what is the wall made of, because that makes all the difference in the world as to the connection type. For example, if the wall is EIFS with styrofoam board, one of the things you want to make sure you don't use is anything with the urethane adhesive in it or sealant to avoid melting that styrofoam. And if the wall is brick, it's important to know that you can only install one anchor per brick. So the anchor spacing of a sign, particularly when you look at this example with these slashes for the AutoZone, they're pretty small, and at least kind of in the center of the sign, they're fairly tightly spaced together. You can only install one anchor per brick. So that anchor spacing is important. Some more channel letters, in this case mounted to a raceway, so it's starting to get a little more complicated. In this case, because those letters are mounted on a raceway, the engineer has to consider the moment or the overturning load of the letters and the raceway on the wall connections themselves. So the fact that they're extending upright, they tend to rotate over, and that's putting added stress onto both the canopy and onto the wall itself where those connections are. If these letters are mounting on top of a canopy, it's crucial to the mounting design to obtain a thorough survey of that canopy frame, including, if possible, any structural drawings that may be available from your client. Example of a wall sign, and in this case, it's a blade sign, which is a type of wall sign. A blade sign is simply a sign that projects horizontally from the wall. In this case, it's fixed. That disc or the sign face itself is hanging down from the bracket and is fixed from the support frame. Other times you'll see that you could have cables or chains or something that is not a fixed connection. And that is much, much, much easier from an engineering point of view. Because this sign was designed as a fixed connection, the wind that's being applied to that sign face torques the entire bracket. If I remember right, this particular sign was being installed in an area in Florida that had very high wind speeds. And so the bracket just couldn't withstand the moment, that twisting motion that was being applied from that face. But the architect insisted that it have that look and feel rather than having chains so it could flop in the wind. And so the bracket itself had to be beefed up significantly in order to make it withstand those wind loads. This is a large wall sign that we did for a site in Englewood, Colorado. It was an existing building. There were good architectural plans available for review. And it's basically the logo, 4.5 feet by 4.5 feet, with some stacked channel letters. One of the twists to this is that, and we'll talk about this in a little bit more, is that because it was located in the corner of a building, so along the sides as opposed to in the middle, you have added wind that's applied to it. So there were several interesting design factors that came into play on this particular sign. This is another wall sign. I call it a big wall sign. It's installed at the Joe Louis Arena in Detroit, where the Nashville Predators like to play the Detroit Red Wings. Technically, like I said, this is a wall sign, but at over 66 feet tall with all the framing and display boards that are built into it and a lot of people underneath, the connection details get very significant. In this particular case, the original design of this building, the arena, did call for these large displays. So you had outriggers that were already in place and designed to handle this. But if you're retrofitting an existing building with one of these large video displays or just a large sign, those support and connection details can get very important. The example here, it's admittedly, it's not really a wall sign, these rooftop signs, but they're not really freestanding signs either. So they kind of fall into an odd place for our presentation purposes, but I wanted to include them here. These rooftop signs can impose significant loads on the roof of a building that may not have been considered as part of the original design. It's important to get the building engineer of record involved for these designs. Your sign engineer can design the sign frame, that structure itself, but the connection of the sign and the frame to the roof should at least be coordinated with the building engineer, if not performed entirely by them. Kind of the way I describe it to clients. In either of these cases, let's look at the one on the right as an extreme example. I can analyze that sign, the framing, and how its loads are applied to the building. That's a really big building, and to build that model and to analyze it out, frankly, you wouldn't want to pay your sign engineer to do that, even though technically we can do it. Much more efficient to get the building engineer, the engineer of record, to make sure that the structure itself can handle these incremental loads from your roof sign. One of the things I also like to point out about the one on the right is that because it's located in the corner, we wrapped around the corner of the building with that screening wall. All that stuff had to be designed. The sign itself is over 100 feet wide. So there were a lot of interesting design elements and challenges when you have it roof mounted. So you've got extra wind pressure from that. You have it at the corner, extra wind pressure, and then you have this frame that's going around a 90-degree corner, the way you design it to fit onto an existing load of a building that had already been built was a lot of fun. Talking about canopies and awnings, I alluded to these earlier. As you can see, there can be a wide range of canopies and awning designs, most of which are relatively straightforward. However, I do like to point out the picture in the middle. When you have a deep awning like this, snow loading and drifting can become a major or the controlling issue. Don't forget, depending on your wall type, for example, if it's an ephes wall, any bolts that hold the canopy to the wall are cantilevered out. That is, that ephes structure is an unsupportive gap between the wall and the canopy because ephes doesn't have any significant structural capacity. That imposes additional stresses on the connection. The 2021 and I believe 2018 building codes start to go into depth in additional design requirements for canopies that haven't been considered in the past. And so if you've been doing awnings and canopies and have a site that requires the current building code, you may be surprised at some of the changes that are just simply required by code that haven't been done or considered as in the past. Marquee signs, I think it's really, excuse me, more of an architectural name rather than a sign name. It's basically just a blade sign projecting out from the wall. But what's fun about these are the challenges, the mounting challenges that you run into. A lot of times these neat signs are installed on historic buildings, either new signs that are being built for a building, or sometimes because the protected nature of the building itself may be an original, restored, refurbished sign itself. And so all the details that you have to get into in the mounting conditions pose a lot of interesting design challenges that need to be considered. Aerial identification signage is one of the recent trends in signage that we've seen for sports venues. Even though these channel letters are mounted to a roof, they would be approached in a manner similar to a wall sign, except in this case, they are huge. They're laying flat, which imposes all kinds of different stresses due to those orientations. This was a fascinating project for all these unusual design elements. The roof penetrations for each outrigger for the letters over a curved roof, which was already built and existing. This was a design element that was added after construction was begun. The sign letters and the logo itself occupy a 200 by 200 square foot area. Each of the letters were about 40 feet tall. The deflection of those sign faces, they were acrylic faces because they're internally illuminated. Normally, when you have channel letters, the face is installed vertically, and you don't really think about how that might deflect. But all of a sudden, you've got a 40-foot long letter and acrylic faces that are sitting within that. They do deflect and sag. How are those going to be supported? If you have internal supports to hold the face up, will that create shadowing effects? How do you physically get the letters up to the center of the roof when the crane won't reach that far? Other things that had to be considered, these letters, the framing of the letters were large enough that thermal expansion had to be considered to make sure that you didn't cause problems with the faces contracting and expanding, creating gaps or cracks within the faces themselves. All kinds of fun things as part of this design. So I want to go into a little bit more refresher about these design loads now that we've talked about some of these different wall types or different sign types and things that you should communicate or that would be good to communicate to your engineer. The dead load. So as I mentioned, the weight of the sign. Is the sign itself made of unusual materials or is it unusually deep? As an example, we do a lot of work with Cracker Barrel and their wall signs are porcelain. And so you've got a metal backer and you've got porcelain applied so that they're pretty heavy. And so that weight needs to be considered as part of the attachment method evaluation. The wind load itself usually controls, not always. The thing I'd like to point out is that just because the building code refers to a particular ASCE wind study map, for example, 2018 building code uses those 7-16 wind speed maps that we looked at earlier. The local authority may have adopted a specific wind speed. We see this where in the building or the local codes, they say 115 miles per hour. It doesn't matter if the design manual is at a lower wind speed, you have to go with what the city has adopted. We also see that in various Florida cities where they don't go by the ASCE design manual wind speeds. Snow load typically doesn't apply unless it's, as I mentioned, a deep canopy or the example we had just previously of aerial identification signage, but you do need to be aware of drifting when it's a canopy. For example, we were analyzing a hotel canopy in Las Vegas, where in the city of Las Vegas, they have a design snow load of 5 pounds per square foot, which frankly surprised me. I didn't think there was any snow in Las Vegas, but that 5 pounds per square foot load is similar to much of the South, or the region where most of us work. Due to the height of the hotel, the snow loading at the building wall, so at the kind of the back end of the canopy, was over 30 pounds per square foot due to the drifting that was applied. That is starting to get significant and actually even resulted in a change in the internal framing of the canopy up against the wall in order to withstand the load. This is typically where we get the most pushback from sign companies that are involved with canopy and awning installation. That snow load didn't traditionally get considered as part of design. It just wasn't required. And so things that were done a certain way may not be acceptable per building code now. And seismic load, as I mentioned earlier, typically doesn't control, but it might. And so your engineer will just evaluate that and consider it. So why does canopy snow loading matter in calculating it properly? These are pictures that we took not too far away from our office back a couple years ago in 2021, when we had a lot of real heavy, wet snows that hit Middle Tennessee. You can see a couple of things from this photograph that I want to point out. One is clearly there was enough snow that the weight was too much. But what you may not notice until you look closely is that the canopy was actually attached just to the brick. They didn't through bolt it or anchor it into the CMU block. And so when that wet snow that we got came, hit those canopies, started drifting up against the wall, the canopy itself, just not only the canopy peeled off the wall, it peeled the whole brick from there up off as well. Always remember, you got to anchor these things into the block itself. Just into the brick is not sufficient for anything of significant weight. Another thing to remember is, what do the local building codes allow? They sometimes will have these weird requirements that you've got to factor in. Two examples that I like to point out. One, a client of ours was looking at a location up in, I believe it was in New Jersey, and the city had a requirement in the sign ordinance that no signage could depict a human or animal form. Our client has got a human form as an integral part of their logo and their branding. And so the city, there was no provision for variances. And so fortunately, we didn't waste much time doing design work for that site, but the city wound up losing a really good restaurant chain because they didn't have variance provisions. But understanding the codes, knowing what is allowed and what's not allowed, and what variance procedures are, was critical in making that efficient. The other thing that we're starting to see increasingly now is a definition of a roof line versus a parapet. We'll give some examples of this in a few slides, but cities are increasingly pushing back that there is a limit to how much signage can project above the roof line. Even if you've got plenty of parapet that the sign can mount to, you may not be able to get the full size of a sign because too great of a percentage of the sign is above the roof that's back behind the parapet. Like I said, I'll show some examples of that. Getting a little bit into the weeds here, but the engineer has to consider the location of the wall on the sign and location of the sign on the wall, and that applies different pressures and loads on the sign. And then obviously wall type, construction, attachment methods are important to know. Speaking of location on the wall, if you look at the graphic of the building, in the center, zone 4, that's the default. You look at the chart, there's a very slight coefficient, this pressure coefficient, that is applied as part of the wind load analysis. Basically a 1.1 factor that's applied. A little bit of a bump up, not much. Depending on the area of the sign itself, it'd actually be a slight reduction. But if you're in the corner in these zone 5 conditions, it's not just a 1.1, it's a 1.4. So that's an almost 30% increase in that coefficient. So that can begin to start to add significant wind pressure to a sign. I mentioned parapets. This is an example from a site that we were working on where you can see in the front, you've got a parapet. And again, you've got framing that's intentionally built up so that the store can use that classic Cracker Barrel wall sign. But if you look on the back side of it, the roof line is much lower. And so some jurisdictions do have limitations as to how much of the sign can be above either a parapet line or above the roof line itself, which is getting close to the base of the sign itself. The graphic on the right is a representation of how those wind loads are applied in a parapet location like this. So you can see There's wind that pushes, if you're going from left to right, wind that pushes and wind that pulls on a sign itself. So these are all things that your engineer is going to be considering, but loading can be fairly complex, and there's a little more involved than a lot of times people think about. I want to talk a little bit about wall types and mounting conditions and give some examples of common wall types and some hardware options. This is a detail we put together for a national sign program project for a client of ours, where they asked us to pre-engineer multiple attachment methods. They didn't know necessarily, this is a rebrand for a client of theirs, multiple locations, and they didn't necessarily know every site what the wall types were. And so we put together these drawings for all the different types, steel studs, solid concrete walls, concrete block walls, wood studs, and that way we pre-engineered it all. We had all the examples. They could send hardware that they need to their installers, and they could permit the conditions with a little bit of flexibility there, so that they didn't have to change things if things were slightly different than they were expecting. Obviously, there are more wall mounting conditions than just these 4, and so there were custom applications, but this greatly simplified and was applicable to a large portion of the sites where they were installing. This is an example of a sign mounted to a brick wall. And it's actually pretty common. Rarely do you just get to attach the sign to the brick unless it's really, really lightweight, such as those flat cut channel letters. We recently had a site in downtown Nashville, some very light letters, and the sign company thought that they had gotten verbal approval for mounting those letters to the brick, just directly connecting them to the brick wall. They thought they'd gotten approval from the city for that. And then, so we engineered that accordingly. It checked out. And so by putting enough anchor points, they could attach to that brick wall. But when they submitted it for permits, they were rejected. With the permission of the client, I spoke with the permitter, and he admitted that mounting to the brick wall worked by analysis, but something must have happened at another site, and they didn't want to take a chance with the brick peeling off. So there had to be a different, quote, more secure mounting method. Through bolts was the answer, put blocking on the inside wall, and everything was fine. But so we're seeing things like this more and more often, where you, unless it's flat cut letters and fairly small, you just can't mount directly to the brick itself. So what kind of information does your engineer need to do a project? This summarizes pretty well, but dimensions of the sign, if it's unusual materials, the weight, if it's a cabinet, do you have any framing information available? Because that helps in specifying where the attachment locations may go. If you can get information on the wall types, that is wonderful, and a whole lot easier than a lot of times surveying and cutting into the walls. The second to last point I like to bring out, do you have preferences for mounting methods? From my perspective as an engineer, there are any number of ways that we can attach to a wall. And so you may have a preference for a certain type of connectors or a certain type of materials that you like to use. Communicate that to your engineer. That way they specify it and they design it the way that you prefer. What about those situations where a sign is already installed or maybe just manufactured? Make sure and survey the site, send photographs with real dimensions, any kind of fabrications details you've got, and how the sign, if it's already been installed, is actually mounted in. We get asked, it's not super often, but it's frequently enough that we get asked to do an analysis of a sign that's already been installed. Maybe they didn't realize it needed to be permitted. Maybe the inspector didn't show up when they were supposed to. Any number of reasons. And so the more information you can gather, the more likely it is that your engineer will be able to analyze and document that what you installed or what was installed actually works. So switch gears a little bit. you've got an engineer that you like to work with, or you can at least tolerate, and they return your calls. So what now? This is an order form that was developed for a project manager at one of our clients that does a lot of program work for AutoZone. It's designed so that the project manager can complete this form as well as possible and email it to us. It has all the information that we need to get things going. Certainly putting together a form like this wouldn't work for just one-off custom signs, but if you're working with a family of signs, it may actually smooth the process of ordering things. And since it's a spreadsheet, everything added up. We've actually, as a side note, we've got an online ordering form that's kind of similar to this, where you can enter in site information. I know several engineers are doing that kind of thing, and we're all with the idea of trying to make it easier for y'all as a sign company to install project requests. Don't forget, when you submit a request, however you communicate the information, to include the site address. Surprisingly, this often gets omitted when someone submits a request for a proposal. We do need to know where the sign is located so that we can figure out what the local building code is. And then layer on top of that, some cities, particularly in coastal areas, have multiple wind speeds across the city. Tampa, St. Petersburg is a good example. And I have no idea what just happened to my screen. I'm sorry. Okay. All right, we're good. That was unnerving. Okay. This is an example of an email that the client who works with that order form sends. I like to give this as an example because it very succinctly communicates all the information that we need. Certainly, you don't have to use this format, but they've got a zip file that has the artwork for the signs. In this case, there were some freestanding signs. They were able to get a geotechnical report. They had photographs. They had other information. And right there in the middle, they've got the address for the site. They did do some research as to wind speed, seismic zones. We always double check that information, but it's great when somebody's already looked that stuff up so that we can compare and make sure that we both get it right. This is a checklist that we'd be happy to send you that summarizes most of the information that your engineer would need. Obviously, we can't capture every situation with this form, but it does get most of it. If we don't get this information, we can almost always make it work out, but more information is always better. And just for reference, what makes a, quote, less helpful order for engineering? An email, and we've received these, with no address, no contact information other than a first name, no dimensions for the sign, or not necessarily less helpful, but perhaps a little more challenging, a photograph, and then basically an email that says, this is what we installed, and the city is now requiring a permit. Can't you make it work out? I want to take a quick look at calculations before we wrap up. Just to kind of communicate with you some things that underlie the drawings and the calculations. I know that there are times when you just need engineering for permitting, and you may even be working with the local sub that frankly won't be looking at the drawings for the actual installation. But why is it good to have those drawings and make sure that your subs use them? This is an actual project that we worked on where the local inspector showed up and started looking closely at the install and noticed that things were different in the field than they were with the drawings. The installation was rejected until we were able to go through and verify that what was actually installed did still check out. Fortunately, it did. I've circled a few things on this slide. On the left side, the dimension spacing, obviously it shows 1 foot 9.5 inches. If it's 9 inches, if it's 10 inches, that's not critical. But what is really trying to be conveyed there is evenly spaced attachments, because the load from the sign is being distributed and the analysis is actually based on a certain percentage of the load going to each connection. So evenly spacing those attachment points and knowing how many attachment points there are that the engineer specified is important as well. In the middle, I've circled actually the diameter and the grade of the threaded rods. Both the diameter and the grade are part of the analysis and the calculations. So using those materials will ensure that it's being done per the design. Similarly, over on the right, you can see the threaded rod going through the double blocking. So in this case, it was a new construction. Blocking was able to be installed at the start, but just making sure that how the drawings are specified is actually how it's done is important. All the engineers in the sign engineering world do our calculations. We format them differently. Some people put it on their drawing sheets. We tend to have a separate attachment with the calculations because frankly, a lot of times the cities don't care as long as it's engineered out. They just assume that the calculations were done and you may not have to submit them. When you do, we've got them as a separate attachment. But anyway, a few things to point out. As long as your engineer is familiar with the design of signage, calculations should be good, but it's always nice to be familiar with them so that you can just spot check things. On the sheet on the left, I've circled in the upper part, those are the loadings that are applied. You can see we've got the wind speed, the building code, risk category, exposure category. Gives you the comfort level that your engineer paid attention and that they looked at the site and they've got the right loadings there. Down at the bottom on that page, you can see we've got 1/4 inch diameter bolts. You can see the loading, the ASD loadings, which is the design approach that's used, and the number of fasteners to make sure that things check out. We like to use red and green check boxes. Green boxes are good. You look at the slide on the middle, the center and the right screenshots are from the wind pressure analysis that we do. Again, you can kind of visually look at it, make sure that the proper wind speed for the area was used. And then if you look over to the right, we've mentioned a few minutes ago about the different zones on a building, zone 4 and zone 5. So this is an interesting example between, and then pushing and pulling, kind of windward and leeward when you've got parapet conditions. If you look at zone 5, for example, the higher wind speed at almost 80 pounds per square foot, as opposed to a lower one at 60 pounds per square foot, that's a big difference and creates a lot more load than it would be on a sign located in the center of a building. Just some information, giving you some background of what your engineer's looking at for you. So in conclusion, hopefully this has explained a bit about the fundamentals of sign engineering and what engineering goes into your wall sign and what your engineer needs to know to give you a good design. The design of a sign can be relatively straightforward, but hopefully you've seen there's also some complexity to it. And if the engineer you're working with doesn't want to know this information, it may be time to reach out to someone else. And there are several very good sign engineers working in this field. As mentioned earlier, we'll have the next session in 2 weeks on freestanding signs, and I hope that you can join us. I really appreciate your time. Please reach out if we could answer any questions that you might have. We do have, well, it looks like I've gone 1 minute over, so I'm happy to stay on if there are questions, but feel free to reach out if there are any questions. We do love what we do. Thank you.